Okay, let's just dive right in. Today, I'm going to be acting as your principal verification engineer. So imagine you've just joined my team, and I'm walking you through an end-to-end masterclass on the Universal Verification Methodology, or UVM for short. Now, assuming you already know the basics of SystemVerilog, you know that modern ASICs absolutely require robust, modular, and highly reusable test benches. And honestly, UVM is the industry standard for achieving exactly that. So we're going to break down how to architect a complete UVM project from the ground up, moving from the basic structural foundation all the way to some really advanced industry best practices. We've got a pretty packed agenda today. We'll be covering the UVM test bench hierarchy, what's inside the UVM agent, transactions and sequences, transaction-level modeling, synchronization with UVM phases, and finally, a really cool best practice using the resource database. All right, Section 1, the UVM test bench hierarchy. Let's start with that 30,000-foot view of our verification factory, because before we write a single line of protocol-specific code, we absolutely have to establish the physical structure of our test environment. Now pay attention, because this is a classic interview question right here. The entire UVM testbench architecture relies on this strict dichotomy between two main base classes. On one side, you have the UVM underscore component. These are your static structural elements, stuff like your environment, agents, and scoreboards. They get built at time zero, and they stick around for the entire simulation. On the flip side, we have the UVM underscore object. These are the dynamic, transient elements. Think of the data packets actually flowing through the test bench. It really helps to think of the components as the physical heavy machinery sitting on a factory floor, and the objects as the raw materials passing through that machinery. When you look at the class inheritance tree, notice how both the static components on the left and the transient transactions on the right fundamentally trace their lineage back to the UVM object and UVM void base classes. This shared ancestry is absolutely brilliant because it's what gives both our static test bench blocks and our dynamic data packets access to those core UVM features, like cloning, printing, and factory overrides. So, building our static hierarchy from the top down, the UVM test is kind of the master orchestrator. It sits right at the top, it's dynamically instantiated at runtime, and it handles configuring the test bench. Inside that test, we nest the UVM environment, which is really just a container that groups our higher-level verification components together. And then inside the environment, we instantiate our specialized UVM agents. These are basically the engine room of our factory, directly managing the interface to the design under test, or DUT. Moving right along to Section 2, inside the UVM agent. Now that we have our environment container set up, let's zoom in layer by layer into the structural hierarchy inside the UVM agent itself. Here is another fantastic interview prep callout for you. An agent encapsulates the protocol-specific logic for a single interface, like a PCI or an Ethernet bus. And depending on whether you're injecting data into that interface or just watching it, your agent will be configured as active or passive. It's pretty straightforward. An active agent actually drives stimulus, while a passive agent is strictly just an observer. To keep our factory analogy going, let's look at the three main pillars of an active agent. First, the sequencer is the dispatcher, arbitrating and controlling the flow of work. Then you have the driver, which is the machine operator. It takes that abstract work request and literally translates it into cycle-accurate, pin-level signal transitions on the actual hardware. And finally, the monitor acts as the quality inspector. It just sits passively on the bus, sampling the pin-level activity, reconstructing the data, and broadcasting it out to our scoreboards and coverage collectors. Okay, Section 3, transactions and sequences. The really crucial point here is understanding exactly what is flowing through our factory. We have our static components set up, so now we need to look at those dynamic UVM objects. I've got to say, I absolutely love this design philosophy. By keeping the test stimulus completely separate from the structural test bench hierarchy, UVM just maximizes modularity. What that means for us is you can write a complex sequence of data transactions once and then reuse it across entirely different projects. You can scale it from block level straight up to system level verification, all without having to rewrite your underlying test bench infrastructure. It's a huge time saver. Let's actually follow the lifecycle of a single data packet. It is born as a UVM sequence item, which is basically an abstract blueprint containing randomized data fields. A UVM sequence then generates a bunch of these items and fires them off to the UVM sequencer. The sequencer arbitrates these items and hands them off to the UVM driver, which finally gets to wiggle the physical pins on the hardware. It's a very clean, unidirectional flow of data. Which brings us to Section 4, Transaction-Level Modeling. These structural components we've just built need a standardized way to actually hand off these sequence items. They need to talk to each other. And that brings us to TLM. TLM is all about connectivity between your testbench components. Instead of wiring up hundreds of individual signals, we just pass whole transaction objects using these interfaces. Now, understanding the difference between these execution methods is absolutely essential. A blocking interface uses a SystemVerilog task, meaning it actually consumes simulation time waiting for the transaction to be sent or retrieved. A non-blocking interface uses a function, meaning it executes instantly in 0 time, though it might return a fail status if the target is busy. And finally, a transport interface does both a request and response in a single blocking call. In order to pass those transactions around, your components will instantiate specific TLM endpoints. If a component needs to send data, it will instantiate a port. You can think of a port as requiring a connection. An export is then used to forward that connection down the hierarchy. Finally, an IMP, or implementation port, is instantiated by the component that actually provides the underlying code to handle the request. So as an example, your monitor uses a port to send data out, and your scoreboard uses an IMP to receive and process it. All right, Section 5, synchronization with UVM phases. With so many moving parts in our UVM test bench, tests, environments, agents, drivers, scoreboards, we desperately need a bulletproof way to keep them all in sync. I mean, if a driver starts injecting stimulus before the monitor is even built, we're going to lose data. So the execution order follows this really strict timeline. Notice how we construct our factory from the top down during the build phase, all at time 0. Then, we wire all those TLM ports together from the bottom up in the connect phase, still at time 0. Only when everything is fully constructed and perfectly connected do we actually start the clock. Now here's a really fascinating distinction. Out of all the UVM phases, only the run phase actually advances simulation time. All the others, they are 0-time functions. The run phase operates in parallel across all components using fork join threads. And to prevent the simulation from ending prematurely while components are still working, UVM uses this really clever objection mechanism. Basically, a component raises an objection to keep the run phase going and then drops it when its specific task is complete. Once all those objections are finally dropped and the run phase finishes, our factory auditor takes over. This is exactly where your scoreboard shines. During the check phase, the scoreboard evaluates functional correctness by comparing the actual outputs from the DUT against a golden reference model. After that, the report phase prints out all your summaries, your passing metrics, and hopefully, absolutely 0 mismatches. Finally, Section 6, Best Practices Resource Database. Now that we've built a complete, working UVM environment, I want to wrap up this masterclass with an industry best practice that will truly elevate your verification skills and seriously clean up your code. Look, sharing configuration data, like virtual interface handles or test parameters, across a deeply nested test bench can be a massive headache. While honestly 90% of engineers out there just use UVM_config_db out of habit, verification experts often point out that transitioning to UVM_resource_db is vastly superior. Here's why. The config_db requires a very strict hierarchical component context, but the resource_db uses straightforward string scoping. That means you can easily access your configuration from anywhere, even from dynamic sequences that exist entirely outside the component hierarchy. So the ultimate pro tip takeaway here is that adopting the resource database eliminates one of the most frustrating patterns in all of UVM, that awkward p-sequencer macro. Because the resource DB doesn't care about component hierarchy, your sequences can just grab configuration data directly. You don't have to route it through a virtual sequencer just to get a component context. Trust me, it keeps your codebase exceptionally clean and modular. So are you ready to build your next test bench using the full power of the UVM architecture? By mastering this separation of components and objects, truly understanding the flow of transactions via TLM, syncing it all up perfectly with phases, and utilizing advanced techniques like the resource database, you are now totally armed with the methodology to verify even the most complex ASICs. So think about the designs you're working on today. What are you going to build next? Thanks so much for joining me in